seen rain, seen sunny days that I thought would never end.
In the first video, we gave the definition of the Maclaurin series and Taylor series of a function. In this video, we'll focus on giving some examples where we compute the Maclaurin series of a function. So let's recall some things from the previous video. If f of x can be represented as a power series centered at 0, what does that mean? That means we can write f of x equals some infinite series, a sum from n equals 0 to infinity of some real number Cn times x to the n. If this function is equal to this series on the interval of convergence of the power series, so for some absolute value of x less than r, where r is the radius of convergence of the power series, then what are these Cn's equal to? These Cn's have to be equal to take the nth derivative of f, evaluate at 0, and then divide by n factorial. So this if is important. Not every function can be represented as a power series where the series and the function are equal, where the power series converges. Stewart's book has some more information about what needs to be true for a function to be represented as a power series, but you don't have to worry about that for this class. We saw a very first example. If you let f of x equals e to the x, then we know the nth derivative of e to the x is e to the x for any value of n. So we evaluated 0, and we'll always be getting 1. So Cn is then given by 1 over n factorial for any n. So what does that mean? E to the x is equal to a sum from n equals 0 to infinity of 1 over n factorial times x to the n. This power series converges for all real numbers x. R is equal to infinity. So remember, we're warning that not every function is equal to its Maclaurin series, the series that you get from this expression, but e to the x is equal to its Maclaurin series everywhere. Okay, so let's do another example. Let's find the Maclaurin series of e to the 2x. And remember the big idea. We'll do the same thing that we did to do e to the x, is we'll compute the first few derivatives and find a pattern. Okay, so what do we need to know? We need to know, well, okay, the 0th derivative of your function is e to the 2x. So that means if you take your 0th derivative and evaluate at 0, we get e to the 2 times 0, which is e to the 0, which is 1. What about the first derivative? Well, we get e to the 2x, and then we get a factor of 2 from the chain rule. So that means we take the first derivative, we evaluate at 0, we get 2 times e to the 2 times 0, which is 2 times e to the 0, which is 2. What about the next derivative? Oh, yeah, let me use this notation for consistency. Well, we have 2 times e to the 2x, and we take the derivative of that. So what we get is 2 squared times e to the 2x. We get another factor of 2 that comes down from the chain rule. So we evaluated 0, and we get 2 squared times e to the 2 times 0, which is 2 squared times e to the 0, which is 2 squared. And when you take the third derivative, you get a 2 cubed e to the 2x. And the fourth derivative, 2 to the 4th times e to the 2x. And in general, if you take the nth derivative, what you get is 2 to the n times e to the 2x, which means if we want to take the nth derivative and evaluate at 0, what we get is 2 to the n times e to the 2 times 0, which is 2 to the n times 1, which is 2 to the n. So what does that mean? In this expression, fn0 divided by n factorial, we see that we get 2 to the n over n factorial. So what does that mean? The Maclaurin series for e to the 2x is a sum from n equals 0 to infinity of 2 to the n over n factorial times x to the n. So again, you can ask, what is the radius of convergence of this power series? And just like we saw for e to the x, you apply the ratio test, and you'll see that it's all real numbers. So this is another example of a function that is equal to its Maclaurin series for all real numbers x. For all real x. Okay, I'll pause and erase, and then I'll show you another way to get to this same expression. So we've seen that e to the 2x, the Maclaurin series, is a sum from n equals 0 to infinity of 2 to the n over n factorial times x to the n. This is valid for all real numbers x. And this looks really close to the Maclaurin series for e to the x. So let's look at this another way. So other way. So we have e to the x equals sum n equals 0 infinity of 1 over n factorial times x to the n. So let's say, what happens if you plug in 2x for x? Everywhere you see an x, instead put in 2x. So what are we going to get? A sum from n equals 0 to infinity. These 1 over n factorials are just numbers. And we just put in a 2x every time we see an x. And here, now we can factor out 2x to the n is 2 to the n times x to the n. So what we get is 2 to the n over n factorial times x to the n. And this is the same thing that we had before. So just like in the previous lecture about section 11.9, starting from the power series expansion for 1 over 1 minus x, we were able to switch variables and get power series expansions for related functions, like 1 over 1 plus x. What we did is everywhere we saw an x, we just put in a negative x. The same idea works here. Starting from a Maclaurin series for e to the x, you can get a Maclaurin series for lots of other things, like e to the 2x or e to the x over 2 or whatever. So I'm going to pause and erase, and then I'll show you one other really important power series that we haven't seen yet. Let's look at the example of f of x equals cosine of x. So we want to find the Maclaurin series, which means we have to solve for these Cn terms. And how do we find Cn? We take the nth derivative and evaluate at 0. So let's take the first few derivatives and look for a pattern. So f, the 0th derivative, just is f of x, which is cosine of x. And the first derivative is negative sine of x. And the next derivative, second derivative, is negative of the derivative of sine, which is negative cosine of x. And then the third derivative is negative of the derivative of cosine of x, which is negative sine of x. So it's negative sine of x, which is just sine of x. And then the fourth derivative is the derivative of sine of x, which is cosine of x. And the fifth derivative is the derivative of cosine of x, which is negative sine of x. And now this is starting to feel familiar, right? Because we already did the derivative of cosine is negative sine. So the derivative of sine will be negative cosine. So the derivative of negative cosine will then be sine. Derivative of sine will be cosine. And we'll just get this repeating cycle. So this repeats. So there's this 4-term cycle: cosine, negative cosine, sine, negative cosine, sine, and so on. But remember, what we need is not just what these derivatives are, but we want to evaluate at 0. So what happens when you evaluate at 0? Well, cosine of 0 is 1. Negative sine of 0, well, sine of 0 is 0, so this is 0. The second derivative, evaluated at 0, is negative cosine of 0, which is -1. The third derivative evaluated 0 is sine of 0, which is 0. And then the fourth derivative is the original function f. So remember, every 4 terms, everything repeats. So we're going to get 1, 0, -1, 0, 1, 0, -1, 0, 1, 0, and so on. So one way to say it is, okay, so remember this Cn is Fn evaluated at 0 divided by n factorial. And what is this going to be equal to? Well, in this 4-term cycle, this is going to be 0 if n is odd. Right, the first derivative evaluated 0 is 0. The third derivative evaluated 0 is 0. All of the odd terms in the cycle give 0. This is going to be Fn0. Well, F0 of 0 is 1. F4 of 0 is 1. F8 of 0 is 1. We're going to get 1 over n factorial if 4 divides n. If it's a multiple of 4, so like if n equals 4 times some integer k, we're going to get -1 over n factorial if 2 divides n, but 4 does not. But 4 does not, which means you're 2 more than a multiple of 4, n equals 4 times k plus 2. Okay. So this is a description of what these Cn's are going to be for all values of n. But what does that actually say about the Maclaurin series? Well, cosine of x, it's the first term is we have the 0 term, which is going to be 1 over 0 factorial times x to the 0 plus 0 times x to the 1 plus -1 over 2 factorial x to the 2 plus 0 x to the 3 plus 1 over 4 factorial x to the 4 plus 0 x to the 5. Maybe a nicer way to say it is this first term is 1, 0, minus x squared over 2 factorial plus 0 plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus x to the 8th over 8 factorial minus x to the 10 over 10 factorial. So the only powers we see of x are the even powers, and they alternate between being plus minus plus minus plus minus, and anytime you see the even power, you have n factorial in the denominator. So there's a nice way to write this. This is a sum from n equals 0 to infinity of, how do I want to say it, -1 to the n times x to the 2n over 2n factorial. Right, because we're only seeing the even powers, and you can check that this -1 to the n is now going to be a plus term when n is even, which means that 2n is a multiple of 4, and a minus term when n is a multiple of 2 but not a multiple of 4. So it'll switch back and forth like this. So let me just point out something here, which is we know that cosine of x is an even function. Right? Cosine of x equals cosine of -x. And this series over here is also even. If you put in -x in terms of x, you're getting the same series exactly. So that's good. You can ask, when is this function actually equal to its Maclaurin series? Well, first you want to figure out the radius of convergence of this power series. It's not so hard to see that it's infinity. When you apply the ratio test, this will converge for all real numbers x. And again, cosine is an example of a function that is equal to its Maclaurin series everywhere that this series converges. So it's not one of those special case weird functions. So this is a really important power series to know. So I want to highlight this one. So this is important power series. This gets added to our list like the first one was the geometric series, 1 over 1 minus x. We saw the power series for natural log of 1 plus x. We saw the power series for arctan of x. We saw the power series for e to the x. And this is another example, the power series of cosine of x. So here we did cosine. You could do exactly the same thing, but starting with sine instead of cosine. And then your derivatives would go sine, cosine, negative cosine, back to sine, and it would still repeat in this 4-term cycle. And you can use exactly this idea to write down a very, very similar Maclaurin series representation for sine of x.